latest IT Leaders survey, it's perhaps no surprise that our leaders see cloud in its many iterations as the biggest and most all-encompassing change that's happening right now. It's the basis for emerging technologies in big data, machine learning, artificial intelligence, blockchain, Internet of Things. The list almost feels endless, as do the threats. When asked what keeps you awake at night, the top answer by some margin was cyber attacks. This was followed by a lack of resources and the sheer pace of change. While COVID has brought devastation to society, it has also brought out the resilience and creativity of humans. In the IT space specifically, we've seen disruption, opportunity, change, and an evolution where ideas have been pushed very firmly into reality. So it's also no surprise that the majority have said that for 2022, their priority is business transformation. I've given you a brief overview there of our recent research report. It will be coming into your inbox straight after this conference, so do look out for IT in your organisation in 2022. Just some housekeeping tips now. We're on Zoom. If you'd like to ask any questions at all, please do type them into the Q&A. Some of the sessions are deliberately designed to be interactive and will encourage audience participation. These include our roundtable sessions on legislation, cybersecurity and sustainability. So let's get to the moment we've all been waiting for and get to the speakers. I'm really pleased to announce that we're kicking off proceedings today with Richard Hopkins. He's an IBM engineer of some 25 years. He's co-author of the book Eating the IT Elephant, which explains how it is possible to modernise complex brownfield IT landscapes using semantic technologies. In 2019, he became the 19th president of IBM's Academy of Technology, and then in 2020, he was appointed a fellow of the Royal Academy of Engineering. Today, Richard is giving a talk entitled Quantum in the Real World. Welcome, Richard.
Can you hear me?
I can, thank you.
Fantastic.
Oh, you're on mute again.
Is that better?
Yes.
Haha. Oh, finally. I've never used the application, always use the browser. Okay, so if I may, I am. Oh, would you like to activate my sharing so that I can share some slides?
Yeah, I'll do that.
Thanks. So yeah, what I want to talk about today is quantum and quantum computing in the real world. It's come a long way as a topic, and there we go. Let's start. Let's do that. And is that visible?
It is, thank you.
Thank you. Excellent. Right. So really what I want to talk about is how quantum has changed over the last decade in particular, from being something that's fundamentally an interesting science idea to something that actually we're now getting very close to the point at which we might actually have something useful. So this presentation goes from essentially from the planetary scale down to the nanoscale. But let's start with the planetary scale. We are a planet with big problems. We grew as a population from about 1.6 billion at the beginning of last century. By the time we reached the end of the century, we were at 6.1 billion people. And that number keeps on going up despite what else is going on in the world. So we have a challenge. This is a little graph that I calculated a few years ago, looking at our energy consumption in terms of terawatt hours. The green bar is our ability to use non-fossil fuels. Our orange bar is our ability to consume them, to consume fossil fuels. Green is green energy. The extrapolation is probably conservative. This is based on the idea that people will want to enjoy the same kind of lifestyle as they enter the middle class around the world as we do in the UK. But I haven't allowed for the additional air conditioning in places that are rather warm. So you can see that even though the population may well level off and the population increase will decrease over time, in terms of our demand for energy, it is likely to grow. And the speed of that green line could really do with some help. Historically, we've only ever managed to switch as a species between different energy types at about the rate of 1% a year. Why is that? Well, I mean, most energy generation capabilities tend to be long-term investments, 30, 40, 50 years, perhaps. And therefore, the actual speed that we've ever managed to change between energy types, whether that's wood and coal and gas and except nuclear, has always been about the same kind of speed. So if nothing changes, nothing changes, and we have a very significant problem, I think. So what can we do that? What can we do as individuals or as organizations? Well, one of the things, other than the obvious of trying to save energy where we can, is to actually change the speed at which we can innovate. Okay, and this is one of the areas that IBM is very interested in at the moment. And one of the key topics we've been looking at is how do we actually accelerate the fundamental scientific process? It's been an interesting convergence over the last few years of AI and big data and cloud and quantum, all coming together roughly about the same kind of time. We're no longer in an environment where when we're doing research, we're just using bits. We're also using artificial neurons, and we're even starting to use qubits. And those different technologies combined give us a very different way to accelerate the scientific process. It gives us ability to look at more possibilities and to understand different outcomes in a way that perhaps we've never been able to do before. So last year, which I think is pretty staggering capability, is we decided to try and find a new photoacid generator for chip lithography. IBM still, although we don't have a fab anymore, we still design and make new chip technologies all the time and continue that research. And what we did was we fully automated the end-to-end scientific process of how we might discover that new capability, that new chemical. Okay, and a process that historically has taken about 10 years, and somewhere between a 10 and $100 million to develop a new photolithography kind of chemical for use in chips. We actually accelerated and concluded that work within the year. We were actually 100 times faster and cheaper. So 2 orders of magnitude may not sound like a huge amount, but in terms of where we're going, in terms of the ability to fuel the next generation of innovation, this is where cloud and AI and quantum combining is going to make a huge difference. And in fact, last year in the UK, we announced our collaboration with the Science and Technology Facilities Council up in Hartpury, up in Warrington, where we've created a National Centre for Digital Innovation. And that centre is going to look at those kind of problems. In fact, we'll come back to those problems later as we go through the presentation. But let's move on from the human scale of things and start delving down into what this talks about, which is the quantum realm. Now, it always amazes me that I joined IBM in the early 90s, actually in 1990. The year before I joined IBM, we very famously wrote the IBM logo in atoms. We used 35 xenon atoms and a scanning tunneling electron microscope, which IBM had invented, to actually spell out our name. That was 1989, everybody. Some of us are feeling very old because we probably all remember that. But never mind, you know, it is now actually routine and commonplace within our labs to actually now routinely manipulate individual atoms, okay? Which is a very, very odd sentence to say, but it's absolutely the case. And in fact, if you want any proof of that, in 2013, we published an actual stop motion animation of a boy and his atom, where literally an animated boy made of atoms is kicking an individual atom as a part of an animation. So, you know, routine, absolutely. But perhaps the most exciting, you know, innovation over the last few years has been that maturation of the quantum computing paradigm. And, you know, we're asking, how real is that now? And how real is quantum computing to real problems? Well, for a start, quantum computing is genuinely real. We are currently executing on the web, on the internet, 3.25 billion quantum circuits every day. So these are the experiments that are being run by scientists, by students, for free, generally speaking, on our quantum computers that are available on the web. 3.25 billion circuits a day. It's giving us a huge ability to kind of to ramp up our capability and tune our systems to make them more capable to tackle real world problems. There are now 24 quantum computers sitting in IBM data centers, and we've got 2 live out with clients, and 2 more being installed. So Germany, Japan, the Cleveland Clinic in the United States, and South Korea have all taken real quantum computers that we've actually installed and are now beginning to use. Amazingly, the Japan one in particular, we actually installed that during the COVID pandemic, which was pretty extraordinary, managing to achieve that level of international collaboration to install the technology. So the technology itself is turning into something that is not quite as lab-based as it used to be, and it's open for everybody to use and to learn. But why should we be excited about quantum computing? Well, apart from the fact that it looks cool, so here I am standing in front of our quantum computer in our research labs. The future is so bright, I had to wear shades. We've now got, you know, these replicas in our new York Road location in London as well, if you want to go around and have a look at one of them. But fundamentally, the reason it's so important is because of Feynman's quote here, that because the world is intrinsically quantum in nature, if you want to actually come up with a solution or a computing paradigm that can predict how either materials are going to work at a low level, or how high energy physics is going to work, or quantum chemistry is going to work, then actually a quantum computer is a very close analog, because of the way it works, to those problems. And it's those kind of problems that are very important from a worldwide point of view at the moment, because it's there that a lot of the innovations are going to be required if we really want to help solve the climate crisis. And just to give you an idea of where this is going, this is just an artist's impression of the System 2. The System 1s have already gone out, are the ones we've already installed. System 2 is the sequel, which you can see there is the idea that we'll have multiple of these machines connected together, and each one of those individual machines hopefully will have, you know, thousands of qubits within it, okay, which will allow us to do all kinds of interesting things. We're not there yet, but where we are is fairly extraordinary, because the whole point about quantum computing is that we're working with, you know, just as we're working with neural nets and working with bits, the qubit can store more information per qubit than a standard bit. In fact, the information it stores is essentially in a coherent state. You know, you're recording a vector anywhere on the surface of that sphere is the information of a single qubit. But more important than that, when you start sticking these qubits together and start superimposing their states and entangling them together, so that the actual information in them starts spreading across the qubits, then you get a very interesting effect where the individual number of states that quantum computer can represent starts doubling for every single qubit that you add to the machine and then entangle. So at the moment, IBM has successfully got working a 127 qubit machine. Now, 127 qubits isn't a lot, okay? It's not enough to really crack some of the kind of problems that I'm just about to talk about, but it's getting close. Why is it getting close? Well, because if you were able to untangle all 127 of those qubits and maintain their coherence for a millisecond or so, then you'd actually be able to create a quantum computer with 10 to the 38 states. 10 to the 38 is a very big number. How big is that number? Well, if you take the age of the universe in seconds, and then you multiply that by the diameter of the Milky Way in meters, that's about 10 to the 38. Okay, so a huge number of states. And the idea of having all those states occupying the quantum computer at once means that you can then start doing some very interesting things with it. So in the real world, what we'll be able to do with quantum computers, well, the very first thing we think is going to happen is quantum chemistry, material science, high energy physics. These kind of things that are very close to the quantum realm will be the first things to actually be a place where we can actually create a machine that will have quantum advantage, which will do things that no other computer will be able to do. But then you move on from that, and it's not very far away from that you start looking at artificial intelligence capabilities. We've already got really quite clever classification systems working on quantum computers that come up with answers that feel very counterintuitive, but it's also a mechanism by which you can do model training, pattern detection, and even, you know, we think some of the early implementations of quantum advantage will probably be in the area of fraud detection around transactions. And then finally, you can take that huge Hilbert space of 10 to the 38 or more as you add more qubits. And the IBM roadmap for quantum computers is that we'll hit 1,000 qubits in about a year or two's time. You can also then start looking at things like optimization problems. So portfolio optimization, risk analysis, credit scoring, and other problems that, you know, currently you probably use Monte Carlo optimizations for. And we've already got clients working on these things. So Mercedes-Benz and Mitsubishi are working using that quantum chemistry end of it to look at battery technologies. E.ON have just joined us, for example, to look at how they might model and optimize the energy distribution network, which is probably going to get more important over the next few years, and how they can balance all of the new ways of both not just consuming electricity but generating electricity. For example, taking energy out of car batteries when they're not doing anything. So it's a really exciting field, and it's beginning to become very real. But why is it so important? Why does it have this kind of planetary aspect to it? And why did I start with billions of people and all that kind of stuff? Well, because some of those first areas that I was talking about, like material science, you know, we spend, you know, the reason we managed to get from 1.6 billion to 6.1 billion people in a century was through the invention of artificial fertilizer. This is the Billingham plant just around the corner from me that produces a lot of the UK's and Europe's fertilizer, for that matter. The Harbour process that runs that operates at very high temperatures and pressures and is not that efficient, frankly. And it consumes worldwide somewhere between, depending on who you talk to, somewhere between 0.5% to 1.5% of the world's energy supply. Now, if you could find a molecule that could catalyze that whole process, you could revolutionize that space overnight. And that's the kind of thing that is really, really exciting about quantum computation and where it might go in the real world. So, for example, you'd expect IBM to so we've just talked about nitrogen fixation and this kind of thing, and we know that there may well be the opportunity for things like better financial models to predict the future and improve portfolios and perhaps improve the stability of the world's financial markets. There's even people who are predicting that using this capability, there's whole classes of new drugs and antibiotics that might be able to be generated. That accelerated discovery process I was talking about at the beginning of the talk, very much applying that to how we start doing how the world starts doing things like drug discovery and the rest. And finally, and probably from my point of view, the most exciting one that I've talked about is the idea of new catalysts, in the same way of changing the way we do nitrogen fixation for fertilizers.